Okay, so with that, and apologies to everybody online, I did not mean to kill the stream. We're going to continue. So wetlands for wastewater treatment. So again, our design here, we want to stabilize it, we want to contain the waste, and we want to remove pathogens. So a typical design, if we're going to install an engineered wetland, is going to have some consideration of like our physical space that we have, right? It's our geography. So we could install a engineered one here, where we see kind of two gravel beds, essentially dug and filled with gravel, and then we're going to let plants grow in and on top of that gravel, and that's going to be a system that is going to allow for a lot of biological activity on the grains themselves. And in this case, if that's the way we're doing it, if this is a gravel system, that would be considered a subsurface flow, where our wastewater is essentially flowing underneath the surface level, right? So that would be and it's kind of hard for me to tell really what this picture is depicting. I think that's what it's saying, and then we would expect to then grow plants on top, right? The alternative would be a free water system, so that it's flowing across the surface, free water surface flow, where you just have a shallow layer of water that's flowing across, and that would be very similar to what you would see in maybe like a tidal flats or some sort of a swamp kind of area, where it's thin layer of water, slow moving water, plants growing anywhere around and in or on it, but you have some water on the surface moving by. Okay, so then your reasons to or your design considerations in general would be, well, how much land area do you have to dedicate to have this wetland? And that's going to, of course, depend on a lot of parameters here. What kind of flow do you need to meet? Is it just one household? And if that household has like one person in it, that's not a whole lot of flow, and maybe you don't need a whole lot of area. If you're designing it for a small village, however, that's a much different concept. And I have a lot of pictures actually from a field trip. I got a chance to go to France right before COVID, and so for those of you who got to come to the seminar the other week with Dr. Geoffroy Lesage, I was part of a collaboration with him, and they took us to an engineered wetland system. I'll show you lots of pictures from that, but essentially they had a subsurface flow system where you had gravel and then this grass stuff growing out on top, and it was for a small community that was like maybe 300 households. So it was a pretty large scale system for in the context of decentralized treatment. Okay, you also have to consider, what capacity for pollutant removal do you have there? What kind of climate do you need, and how much variability can you handle in terms of what's the coldest temperature, hottest temperature, things like that. The types of plants you're growing are going to have to consider that. Going to have to consider what treatment levels do you have to achieve, right? If you're going to design this, just like any wastewater treatment process, you have to consider what's downstream and what level of protection do you need to provide with your effluent, right? Now, in the context of a house in the middle of nowhere in Nicaragua that just wants some better sanitation, maybe it just is better that you have something rather than nothing, right? Maybe that's your end point. But if you're going to design one of these and implement one of these as a regulated infrastructure, you certainly have to make sure you're meeting the prescribed treatment requirements, and consider, well, what happens if you're not meeting those? Do you have a backup plan? Last thing here I'll mention is you really want to keep a separate hydrology from the rest of the groundwater, because you don't want your wastewater process to just seep straight into your groundwater, and then you might as well not be treating. You might as well just be discharging into the groundwater at some point, right? So you certainly don't want that, and then that means you typically are going to have some kind of a liner as part of your installation. Okay, quick note on the biochemistry side of things, and we'll probably get more into this in the waste stabilization lagoons. But essentially, we've got a couple different types of bacteria that are going to be doing the processing for us, the waste removal. So chemoheterotrophs, organisms that are going to use the organic matter as the energy source, carbon and energy source. And under aerobic conditions, so when they have oxygen, they'll be consuming oxygen, doing typical respiration like we do when we eat something, or organisms inside of us and ourselves. Basically, taking that oxygen, taking the organic matter, creating CO2 and water and heat, or otherwise, adding cells and all that. Okay, so then alternately, chemoautotrophs, so rather than chemoheterotrophs, hetero meaning they're going to eat something else, but chemoauto meaning they're just going to find energy or find their carbon source themselves through CO2. They can actually take CO2 and essentially use that as a carbon source, so then we can get some ammonia removal that way, or denitrification. So we take ammonia, and so this is dissolved CO2, so bicarbonate here, and oxygen, and we're going to end up with nitrate there. Probably get some nitrite first and then nitrate, CO2 and water and heat. So we've got those organisms as well, and that's really nice because one of the main concerns in any wastewater treatment is what happens to the ammonia. So if we don't have anything that's taking care of ammonia, then that's discharged downstream, and ammonia is toxic. So we don't want to leave that to the downstream organisms to deal with, because we're trying to protect whatever is downstream, right? That's the point of the wastewater treatment. Okay, so then if we're looking for complete nitrogen removal, there's maybe some possibilities to do so. Certain genus, Pseudomonas, can convert nitrate into nitrogen gas. So that's technically denitrification. And if you have the conditions right, this is what it would look like. You have some sort of a organic matter plus nitrate to yield nitrogen gas, CO2, water, and a bit of ammonia back into the system. But presumably we're converting so much ammonia into nitrate and then nitrate into nitrogen gas that the net is a good benefit there. Okay, so free water service. How do we manage them? What do they look like? And what are the considerations? Well, first of all, we understand that we're going to have low dissolved oxygen in some places. That's going to be zones 1 and 3 here, where we have first of all, let's say the water is going to flow this way, right? The inlet here, we've got it distributing across all sorts of plants here in zone 1. So it's going to be a shallow area, and then typically we're going to have some area that's open to the atmosphere. It's just an open channel, so we intentionally keep some of the water open. Might even have some fish in there, as this is showing. Maybe this might actually support all sorts of aquatic biological life, right? So if we have this water and it's not too awful, some things might be able to live there, and that's I guess no problem, assuming you're not really going to be in too much contact with that, or pathogen transfer, or if this is a large-scale system, you might have to start having concerns about heavy metals or something like that. But in a small system, maybe that's no big deal. Perhaps you have some submerged plants if they're able to grow there, but what you expect is low dissolved oxygen in this vegetation zone, where you've got shallow layer, not a whole lot of mixing, a lot of shelter. The plants themselves probably are producing oxygen, but up in the leaves, and then at night they may be actually consuming oxygen and probably shielding the water itself, so there's not a whole lot of algae growing, because most of the photons are taken. Then you get to the open water, and then you have more potential for algae to produce oxygen. You have more potential just simply to have mixing with the atmosphere. If there's any kind of a breeze, that's going to give you a little bit more mixing on the surface. And so that's going to be a sunlight zone and providing dissolved oxygen. So whatever bacteria are in the water column there have a different set of solution conditions to work with. They've got more oxygen there, and they've got a bit more mixing, and they've got sunlight. So you've got most likely algae, cyanobacteria, in addition to your heterotrophic bacteria. Okay, so then you've got from there another vegetated zone, and then an outlet. And what you'll notice here is this outlet's coming out from the middle here. So it's essentially, we've got some kind of a soil, but it's pretty much saturated with water this whole time, right? So it's allowing for marsh plants to grow. You wouldn't be able to grow typical plants because their roots won't be able to handle it. They'll essentially decay and die. But for plants that are kind of designed, so to speak, to thrive in that kind of condition, you can get those, you can have those living here. So essentially the combination of the plants taking nutrients, all the microorganisms in the soil consuming nutrients, all of those things combined, you're getting a processing of the waste, so that by the time your water reaches the end point, which you can imagine, you can of course extend this wider this way, but you can also go farther deep into the page or out of the page to expand your land area, right? So really this picture is just a slice here. You can certainly have a very large area and that means you can have a very low residence or a high residence time. So your wastewater that you discharge into there may stay there for a very long time before it ever finds the outlet. Maybe the outlet's not just one pipe, maybe that's a series at the end or something to that effect. Your inlet usually will be one pipe but distributed. So maybe a pipe that's perforated along, maybe it's a pipe like this that's got holes in it and is essentially allowing for discharge into the system across a range of spots. So it's not just one fast channel pushing into the water. So whatever the case is, that's kind of the free water surface system. Pretty standard. You just want kind of one zone that's vegetated, one zone that's open water, and then another vegetated zone. What you want to use for the soil, by the way, is something kind of like a sandy loam type of soil that's lots of porosity, easy for plants to grow into, and kind of is not going to just be straight up thick mud, right? It's probably going to become that over time. So maybe at some point you might have to add in more sand or exchange sand for the stuff in there, because chances are all this biological activity, all this sediment stuff might shift this more towards loamy and mucky than sandy. But really you want a decent balance for that. Okay, so then a subsurface flow, or also known as a reed bed. So these designs are a little bit different in that you don't really have water exposed to the air at any point. In a way, that might actually be very nice, because that means you're not going to have as much smells coming off of there. But it's going to also potentially be a challenge if you're, concerning aeration, so providing oxygen to the system. Okay, so essentially what this will look like, and this is actually the type of system that I've got some pictures from, is you're going to have maybe half a meter or so of gravel media, probably a bit more than that. So you have the gravel media forming some surface, and then you're going to have plants growing out of that gravel, and they're going to send their roots down, find the water, and essentially you're going to have gravel acting as a substrate for biological attachment, so it's sort of attached to growth. The bacteria will attach themselves to the surfaces of the gravel, and so you'll have biological treatment from the bacteria there. You're also going to have these plants, lots of plants. Typically these will be like fast-growing grass-type plants, growing on with the roots down into there, which may provide some utility in addition to just the treatment, by the way. So if you can grow something that you can burn as a fuel source or transform it into some sort of fuel source, that would be a good idea to do so. So you get a biofuel out of the process, perhaps. But at any rate, they're going to be withdrawing lots of the nutrients. That's going to help with the nutrient aspect of the treatment. And generally, just the combination again of the bacteria plus whatever the plants are taking up, that's going to give you treatment, reduce your oxygen demand, and all that. Okay, so typically this will have, you have an inlet zone where you're sort of letting the flow stabilize. You're probably not growing plants just yet. You'll have then the zone 1, zone 2, and zone 3. That last one would just be, I guess not 3 technically, that's just an outlet there where you collect what's coming out. Throughout this process, the water is maintained below the media surface, as you see. So you'll have some sort of water, and you can kind of see you can slope it so that the water level itself ends up sloping as well, and then you keep essentially a flow of water heading that way. Okay, so most of what I'm going to show you today is just pictures from my trip to France. This is Montpellier down there, so that's where Dr. Lesage came from, and the site that I'm going to show you was essentially from kind of a suburb sort of a thing, away, maybe half-hour drive or so away from Montpellier. So that's going to be a small village. I think it was maybe 300 homes up on a hill. And the idea here was to treat water for this entire village. So in addition to that, they also had it set up to do kind of experimental side projects. So I have a few pictures of essentially what it looked like, or what they had set up to grow lettuce, to see how much contamination was going to the lettuce. Of course, they're not planning to consume that. That was probably just discarded as waste. But they're testing, okay, well, are the heavy metals accumulating in the lettuce leaves? Like, could we potentially use this, I don't know, to feed rabbits or something? Like, the thinking here is, what can we reuse and what can we learn about these different activities? Okay, so this is the intake for the plant, and what we see here is we have a mechanical screen system where all the junk that could clog up our gravel is being screened out and discarded through this system into a trash bin, and you can kind of see a bit of the junk there. Whatever kind of flushable wipes or similar that made their way into the toilet system, which shouldn't, don't flush flushable wipes. That's what this is catching or attempting to catch, and this is kind of our front end system. Also kind of makes you think, well, if you are going to employ a system like this, let's say a small scale wetland treatment system, and you do have to have, like, if you're going to do that and you have to have a system like this, well, that's already starting to be a bit technologically intense. So probably a good decentralized infrastructure option, but it's still a fair bit of infrastructure, right, and maintenance required. Okay, so this is just taking a step back here. This is kind of what the area looks like. I think off over to this side is where the intake is. We have several wetland beds here, and you see they've got a liner here, and the bed itself goes off that way, and another one over here. They have lots of these little tubes that are essentially PVC pipes that are inserted down into the gravel, into the water, and essentially these are just pipes allowing a bit more airflow, so there's going to be aeration. I think sometimes they will drain these completely, and it may be sequentially, so that part of the time they have that water level up next near the top, so maybe 6 inches, 10 inches away from the top of the gravel, and then they would drain it and essentially allow aeration by letting one drain and then fill back up. I think that was one of their processes. Maybe that was something they were testing. Okay, but this whole plot of land here was contained, I think, 4 of these large wetland beds here, in addition to a few kind of pilot scale stuff. So another image here, seeing the pipe, PVC pipe going straight into the mess there. And they also had a sprinkler system. So this almost looks like a little bird there, but that's a sprinkler system to spray some of this wastewater from in there to just go over top of it. Another aeration strategy there. I think that's you can also see that right here. Okay, so this, I think this is after that screening chamber. I think this is the input well, or the input cistern, I guess. And so I think the water is going to be pumped from here into each of the wetland systems. They had some cool science kind of demonstration sort of stuff, all in French. I'm not by any means able to read or speak French, so can't really describe all that to you. But you can tell one of the purposes for this whole thing was to say, okay, well, we've got wastewater. What can we do with it? Well, we can treat it with plants, and then what else can we do with it? We've got microfiltration. We've got electro-oxidation, membrane, gravity membrane, UV reactor, and I don't know what else. But essentially we have them showing that, like, hey, we're exploring these different technologies, seeing what could be possible, and then maybe we have possible water reuse directly, or maybe just kind of like gray water reuse type of situation where you can irrigate with it. So I think that's kind of their big scheme here. They're showing they grew some lettuce, so they're exploring like what kinds of parameters here are a concern or are maybe promising in terms of what they're finding. Okay, and they're doing that by piping the effluent through these systems into all sorts of these different containers. So of course, I was visiting in December, so it was a bit chilly, and they didn't really have too much ongoing produce production at that time. But a pretty neat system, and what you see in the background here is essentially, it's like a container, like a shipping container that you see on the back of a truck or on a train cart or something like that, except they have several different these water treatment, I guess the post-wetland treatment systems to see, okay, well, if we do this kind of filtration or if we do that step, how much of the pharmaceuticals that end up in this water, can we trace those, and can we find that they are now prevented from being in the lettuce, or are they present in the lettuce? That type of question. So here in the corner is Jeff Waugh, and Madhu here was my PhD student who just graduated this semester, or just defended his thesis this semester, will graduate in May. So he was there for a semester working on some projects, and so he joined us for that tour. Again, this is like right before COVID, so December 2019. And what we see here is, I think, a control system for one of the processes. This might be one of the membrane systems, and then storage tanks for filling water to test the treatment or to be a source of feed for the treatments. And I think right here, kind of behind this little panel, is a gravity-fed ultrafiltration membrane. I think that's what's happening there, and so we're testing that out. And this is, by the way, this roof is the structure we saw a moment ago back here. So that's inside this little box. Oops. Sorry. Okay. I have another kind of interesting case for you. There's another wetland treatment system in Mandeville, Louisiana. So this one is more of a natural system, which is going to act a lot more like the open channel thing. So the Mandeville has a permit for up to 4 million gallons per day for their water treatment, although their typical flow is 2.3 million gallons per day. And essentially their treatment consists of 3 wastewater stabilization lagoons. Talk more about that next time. Just a quick and dirty description though, when you have the stabilization lagoons, depending on how you design them, you'll have the water, you'll end up with some layer in the water that is, you have oxygen, and then some layer that's anoxic, typically. And certainly the muck at the bottom, there will be anoxic processes there too. So in some sense, stabilization lagoons are relying on a combination of so aerobic and anaerobic processes and some interesting biochemistry at the interface there to do a lot of the processing. So that's, yeah, and then you just give it a long time sitting in there, right? So that you get a fair bit of treatment just putting it into a lagoon and letting it sit. So anyway, they've got 3 stabilization lagoons, and then they do UV dosing at the end, and then from there they discharge it into a wetland system with the intent of letting that wetland system kind of finish the treatment, polish the treatment, and then it essentially runs off into Lake Pontchartrain. So it's an interesting system in that, you know, if you were to just think about taking the 3 wastewater stabilization lagoons and then discharge straight into Lake Pontchartrain, that maybe you could get a permit for that, and maybe that's sufficient treatment, or maybe you need slightly better treatment than just that. So if then you consider taking the wetland system and discharging to that, then look at the effluent as it's reaching Lake Pontchartrain. Well, first of all, it's kind of harder to tell what is this water quality compared to what it would have been, right? There is a natural wetland system there. There would have been water making its way to Lake Pontchartrain anyway. That has some sort of water quality. And so you start thinking about it, and it becomes a complex problem to really understand what kind of treatment is happening and what level of treatment do you actually get. Is that appropriate? Are you harming that wetland itself? Is that okay? Is that not okay? And this is a 1,700 acre system, so it's not a small piece of land. Certainly some possible concerns for the wildlife or for the wetlands themselves. Okay, so then the way they do it is and actually they have two natural wetland systems, sorry. The way they do it is they disperse it with multiple outfalls, is what we'll call them, where the points of discharge, and those are going to disperse the flow over a wide area. So it's not just one big pipe leading into a wetland and then it's just finding its way from there. They have a series in each wetland that they use, a series of pipes, so to spread the flow out across a wide area. So this is what it looks like. Get rid of that. So essentially we have the wastewater stabilization lagoons. I think what they consider is these are the lagoons here, and then these two I think are just kind of additional holding tanks or holding lagoons perhaps, where they're going to discharge from there. Maybe they just treat this one here as just one, but what you can see even from this like Google Earth image here is in these three here we've got aeration. So these are fountains or something that's spraying water up and around. It's wastewater, by the way. So I believe all three of these are getting aerated and mixed to an extent. You can also see a lot of algae, cyanobacteria growing, kind of visible from here. And then essentially these will be collected and then be treated with ultraviolet light and then discharged into the surrounding system. So if we take a look at Lake Pontchartrain here, Lake Maurepas, essentially what we're talking about is an area right here near Mandeville, and that is kind of this blown up picture here. And so really the wetland areas, we can see again that picture of the wastewater treatment plant, that is then discharged. I think most of the flow goes into the wetlands here. And I think maybe there's another wetland kind of over this area, distinct. But you can kind of see this one channel, right, going through. And so essentially it's making its way into that. And so they probably have outfalls all along here or something like this. And I think maybe even they have a boardwalk there for it. Been meaning to tour that. I have not done so yet, but may set up something like that in the future. So anyway, that's a lot of the wetlands right there being treated or helping to treat that. And of course that's going to make its way into Lake Pontchartrain there. So that's a more local situation using a natural wetland system, and you see, at least with that one channel there, we are going to have some open water treatment before it ultimately reaches Lake Pontchartrain. So yeah, there's a lot to think about there in terms of the amount of flow, what kind of area we're using, and what kind of treatment we're accomplishing before we send it out to the wetlands. And should we treat the wetlands as a receiving water or as a part of the treatment? You know, that legal-wise, that there's some important questions there. Okay, so flashing back just briefly to the place in France, considering like how to design a system, if you're doing an engineered system, you have to have a liner. So we see that's why I've got this picture here, this liner. And typically you're going to want that to be something like 0.7 millimeters thick, or that would be called 30 mil. That's essentially one 1/1000th of an inch. Maybe you want thicker, or to go on the thicker side of things if you can. But if that's not available, you could potentially add sand over rocky areas to try to smooth it out, try to help prevent any tears. Because really what you care about is you want this liner to prevent your wastewater from getting into your groundwater until it's had sufficient treatment. Now, of course, in the example of the natural system, where we're just discharging into the natural system, that's why they do the UV treatment first, presumably to get rid of most of the pathogens. Okay, so we want to protect the groundwater, and another thing we want to do is protect the treatment system from being not contaminated, but infiltrated by groundwater itself. So if we have, let's say, a rainy season, suddenly all that groundwater is coming from the ground into our treatment, that's going to add a lot more flow rate than we were expecting, and then that's going to push our treatment process, it's going to reduce our treatment time, essentially. So we don't want that either. Okay, got some information from it's the book I was taking this information, or a lot of materials from. I think this is actually in our book. Just basically a comparison here about kind of what kind of exposure, or so we've got wastewater exposure there, the hydraulics, bedding requirements, effluent zone dimensions, and what kind of a grade do you need for the bed bottom for the different treatment types. So you need a higher grade for a free water surface than you do for the gravel system, in part because you're sort of filling up a tank, and you just take the outlet, you're going to be able to have that volume to work with. Lots of different pieces of information there. We kind of touched on basically pretty much all of this, I think. There's some recommended dimensions here. If you wanted to go off and design one yourself, you'd want to find some reference material like this, and probably more detailed than this. So I'm going to leave that there for the moment, but as you can see, there's just a few different considerations for the different systems like we've been talking about. Okay, so what about wastewater constituents? Like how well do they do in terms of removing? So here we have the free water surface system versus the subsurface flow. And if we take a look at a few different parameters, we may find some interesting things. So first of all, pathogens we expect to be reduced, and not necessarily killed, but just sort of removed. Maybe physical processes where they get stuck to things, maybe they're outcompeted by other organisms, so there's just other organisms that end up preying on the pathogen species. But we can expect 99% of them to be removed. Decent removal, certainly not something you'd want to be drinking afterwards or anything like that. Nutrients should do a pretty good job removing nutrients, total suspended solids, and of course biological oxygen demand. So just taking a quick look at a few of these, here's a free water system with 172 milligrams BOD per liter, and that treatment, after treatment from a free water surface wetland, became 12 milligrams per liter. So talking about BOD, if you're above 8 or 9, you're still at a point where you could potentially cause an oxygen deficit that's meaningful, right? Because our standard or dissolved oxygen in my water bottle here is bound to be something like 8. It's not particularly cold, it's not particularly warm. It's probably somewhere between 8 and 10 milligrams per liter. So if something were to start removing that and was able to remove 12 milligrams in every liter, if I kept it sealed, this would go anoxic and would still have some BOD stuff in it, or oxygen demand. Of course, hopefully there's not that much biological activity in there anyway, so hopefully I'm safe from that. But just giving you the conception here, what that means. Now, if you were to discharge 12 milligrams of BOD per liter into a stream or river or something, chances are good there's going to be some aeration. It's not going to be a problem. It's not going to cause that big of a deficit. But I'm just kind of giving you that frame of reference, right? Whereas 172 is quite a lot. Okay, and that translates to 93% removal. Okay, so let's just go down the line for the free water system. So the total suspended solids started at 185, going down to 14, similar, about 91% removal. Ammonia, so nitrogen ammonia, went from 32 to 3.8. So we're getting about 1 log removal for most of these things. Phosphorus as well, 3.8 to 1.8, well that's only about 50%. And most of our regulations now have phosphorus regulated at 1.0 milligrams per liter. I think it's starting to, in some places, be pushed lower. Phosphorus is a big contention, especially in farmland areas. Concern about eutrophication and all that is a big deal, and it's really hard for farmers to apply fertilizers and keep them in their land. They want to because it's going to waste money if it's discharged out away from their land, but it's a difficult and contentious issue for anybody in the farming field as it relates to wastewater discharges. And if you look at the our regulations, we specifically exclude agriculture ditches from being waters of the state that are regulated, right? Because they end up filling with fertilizers when there's runoff or when they're irrigating the plot of land, and hopefully or presumably they're going to try to reuse a lot of that, the ditch water, but it's just, yeah, difficult managing. You're adding these nutrients that really you don't want in your water, but you're using water to convey it to the farm, or the farm's got those and the water. All right. So anyway, let's take a look then at the subsurface flow, at the percentages here. If we have something similar in terms of a wastewater, it's a different scenario, but it's a case studies here. We've got 93% removal of BOD, so pretty much same there. Not as much removal of total suspended solids in a gravel system. That kind of may make sense because you don't have water flowing through that sandy loam stuff, right? If water's going through that sandy loam stuff and having that area to sediment, it's going to be a lot different than flowing through a gravel bed, right? Flowing through the gravel bed will provide lots of opportunities for sedimentation to occur within those pores, but you're not going to have as much absorption as you would have if water's significant amount of your water is going through that sandy loam material. Ammonia nitrogen got 94% removal, so a bit better, and phosphorus a bit better there. So if your primary concerns are nutrients, then perhaps the subsurface flow is better. If you are a little bit more concerned about your particles, then maybe your free water surface method is better. Okay, a few plants. Of course, if you're thinking about what type of plant to make use of in these different systems, the type of system is actually going to be very important, because you don't want a plant that really can't handle anoxic conditions. You don't want to use that in your free surface water system, because then, like I said earlier, the roots are going to rot and they'll die. Likewise, tends to be better if you're using the gravel system to have something that can put its roots down deep and just extract as quickly as they can. So for a free water surface, we have bulrush, cattail, common arrowhead, papyrus, and yeah, so those ones are common. And if you're familiar with any of those are typical plants you find in the swamp, right? Cattails have the large brown seed pod sort of a thing. Maybe that's a fruit. I don't actually remember what that is. But you've seen those, and they grow in swamp areas, wetland areas. So you're going to use things like that. For the subsurface flow, you're going to use grass-type plants instead. So torpedo grass, common reed, rush, sedge, yellow flag, umbrella palms, wild canes. So there's all sorts of things here, and if you think about it, maybe there's room to kind of innovate here. Maybe you can grow something as a biofuel, and in which case you're not really concerned about pathogen transport, because you're going to process it and it's not going to be used for consumption. Okay, so any questions on wetland systems? Yes?
Is there any difference between wetlands or marsh and a swamp?
So essentially, those terms are synonymous. So marsh, swamp, wetlands are all fairly synonymous. Maybe there's some technical definitions that are different. Here, really what we aim for if we're designing it, if we're doing an artificial style, is one or the other in terms of like having that engineered control over what exactly is happening. So if you go out into nature and you think, okay, I'm in a wetland or am I in a swamp? I'm not sure. Maybe there's a distinction. Does anybody happen to know if there is a distinction there? Yeah.
I think it kind of depends, like, marshes are more, can be more coastal.
Okay.
And like swamps kind of more like bayou, kind of stuff like that. Wetlands are
Yeah.
in the north too.
So a marsh is often associated with like a salt marsh,
Yeah.
where it's like brackish water, salty water, and you'll have different types of, saline plants that can, discharge the salt concentration. Yeah. So maybe marsh is more often used in that respect, but I want to say it's like not mandatory that it's used that way, but like
Yeah.
definitely that has that connotation. Yeah, maybe swamp might convey that it's a little more like covered with water or mostly covered with water, but I think it's
I think it's mainly just like a southern thing too.
Right.
Also, like, you don't really hear about swamps in the north as you go to the north.
yeah.
I don't know.
Anything else? Any questions? Okay, so my plan. So next time we'll have a talk on the waste stabilization lagoons. See if I can just go back to the Kahoot here. So waste stabilization lagoons next time, and then I'm going to start trying to add in some questions, kind of like, we have a little bit of time left today, so if I had been prepared, I would have given you a question, say kind of, hey, this is the type of thing maybe we could look at on an exam, related to the content, but require you to synthesize a few different things, look at a little bit of math. So we haven't taught you any specific math for this class, but you're all engineers, so I expect you have capabilities, right? So I'm not going to require anything of you, that you had memorized a formula from another class or something like that. If you needed something, I would give you something. But basic, just kind of sense making of environmental challenges, and then articulation of, well, what kind of considerations might you have socially or economically or something like that. So I'll give you some examples over the next few sessions. Let me see if I can go ahead and not sign up for whatever Kahoot wants me to do. Okay. So for today, we'll just take attendance and let you be on your way. And remember, the paper is due tomorrow night by midnight, and I want that on Moodle as a Word document. All right. Have a good day. I'll see you guys on Wednesday.
Sure, thank you.